So in this video, I wanted to tie up some loose ends on the one-dimensional well. So let's look at the finite well. The finite well would look more like this. From 0 to L, you're 0 between 0 and L, so U is equal to 0 when X is between L and 0. But outside that region, it's not infinite. It's just, let's call it U naught, some constant. So U is equal to U naught elsewhere. Well, I'm not going to work this thing out in detail. I'm going to tell you how you would work it out, but I don't want to spend the time on this right here. And first of all, what you'll notice is that there won't be an infinite number of bound states, because the lowest energy might be here, then the next one up here, next one, so on. Once you get above this level, the total energy, once you get up here, you're free and you can go out and you're not discrete anymore. It's a continuous quantity right here. But we would only be looking at bound states. So now you ask, what does the wave function look like? Well, for the lowest state, remember, if the energy is down here, or below here, then we know on this side, whenever U is bigger than E, you're going to be kind of going off like this, right here. It could be coming in from the bottom, which is identical right there. Same with over here. It'd be going off like that. Remember, for our infinite well, this went all the way down to 0 right there. And then, and then in between here, you're concave down, so the lowest state would probably look something like this right here. There's the lowest state. The next one up above that would just have an extra wiggle in it. It'd probably go like that right there. The one above that one, the third one, would have an extra wiggle in it. Sometimes they call them extra nodes, and so it would be like that right there. And then you'd have the fourth and the fifth and so on right here. And we know the solution in this part should be the same because U was still 0 even for our infinite well. And so in this region 2, A psi in region 2, just like we did for the infinite well, it would be something like an A cosine. I think before we had the square root of 2m E over h bar x plus b sine square root 2m E over h bar squared. Actually, I'm going to change one thing here just to make it a little easier. Instead of going from 0 to L, just to make it a little more symmetrical, maybe I should have gone from minus L to L and put the origin right there. That way everything is kind of symmetric. So it doesn't change anything over there. So this is just going to be minus L. Minus L. So my origin is right there instead of right here. So this would have been from minus L right there. Okay, so that would have still been psi of 2. Now, over in this region, we said it's just going to die out exponentially right here. Psi of 3 would just be some AB, that's another constant, e to the minus alpha x. It just dies out right there. Where alpha would have been the constant right there. The alpha would have been the square root of 2m over h bar squared u minus e minus u minus e. Okay, because we have a U naught in that part. Okay, and then over here, it looks like it'd probably just be a positive exponent. Actually, I probably don't even have to look at this region because everything's kind of symmetric. So whatever happens over here is probably going to happen over here. But if I did say a psi 1, I'd probably say something like d e to the alpha x. Okay. So those, those would be my wave function for the different pieces. And then we would just have to find all the constants. I would have to know what A is, B is, C is, D is, and E, what the energies are, eigenvalues. U naught was a constant, but the energies are going to be different. Well, how do we get all of those constants right there? Well, you'll notice right here that this wave function, at least in here, this first one just goes along like this. It's symmetrical about the x-axis. Everything on the positive is the same as on the negative. And we would say that's a symmetric solution. The blue one right here is anti-symmetric because when you flipped it upside down. So that's an anti-symmetric. The green one is back to symmetric again because if you make a mirror image, it's the same. And the fourth one would be anti-symmetric. All the symmetric ones would just contain that term. All the anti-symmetric ones would just contain that term. So I could break this up and say, well, why don't we just look at the symmetric terms, the symmetric states right here, symmetric. It'd just make it a lot easier, symmetric states. That's where I would say psi 2 is just the cosine. I would just use that one term. A cosine square root of 2me over h bar squared x. And for the anti-symmetric, I would just say psi 2. Psi 2 is just your b sine square root of 2me over h bar squared x. So I would say, okay, now if we look at the symmetric states, what do I have? I have this, and I have this, and I have that right there. Now I say now I have how many unknowns? I don't know A, C, and D, and E right here. So I need to get at least 4 equations, I think. But I can get those because didn't we say that the function has to be continuous? So that means psi at 3 at L, psi 3 at x equal L should equal psi 2 at x equal L. X equal L. There's an equation. Also, the derivative should be the same. The derivative of psi 3 dx at L should equal the derivative of psi 2 dx at x equal L. At L. Okay, and also I could say, I could also say that when you square this function right here all the way out, the total area should be 1. So the integral of the full psi squared dx has to equal 1. And then I could have said that this one has to be match up and the derivative of that. That gives me enough equations to get A, D, C, and the energies, all the eigenvalues right here. And I could do it again with this one, and I could do the same thing. I could say for these anti-symmetric, The function has to be continuous, the slope has to be continuous, the function has to be, the slope has to be, and the total area has to be 1. It's enough equations to calculate all this so I can get all the size and I can get the energies. Now you won't get an infinite number of them, because eventually as you keep plugging in more and more here, eventually your E is going to be above U naught, and you can only take the solutions that are below it right here. It's a lot of algebra. I'm not going to work out this right here, just because it is a lot of algebra right here, but you can see how to do that. First of all, what you're going to notice about the energies, you remember our lowest state for the infinite well was like this right here. It went to 0 at these 2 points. Well, you notice this one has a longer wavelength. Longer wavelength means lower energy. Remember, because we know E equals hc over the wavelength. If the wavelength is bigger, the energies are a little bit lower. So what you're going to see is, as you make this down a little bit lower, as it becomes smaller and smaller here, these energies will get a little bit lower right here, and the wavelength will get bigger right there. Okay, another thing you might notice is what happens if this thing doesn't go off flat forever? What if all of a sudden it came down and it went off like this instead, right there? Well, you'll notice there is still a probability of finding it out here, because it didn't go to 0. I mean, it went down to here, but it's from right out here. It should be back to wiggling. Because why? Because U is 0, it's like a sine wave again, so it's going to be off like this now. So you have a probability of getting through a barrier right here, which classically would be impossible. Why? The energy is way up here. You don't have enough energy to get out of it right here. But quantum mechanically, you can, what they call tunnel. You can tunnel through things and make it out the other way, because that wave function, that wave can penetrate out further. Remember, that wave is a probability of detection right here. So this comes up in a lot of places. If you look at something like alpha decay. Alpha decay, you get a uranium, 92-238. It decays by throwing off an alpha particle. An alpha particle is 2 protons, 2 neutrons. That would be a 2 and a 4. It's 2 neutrons, 2 protons. Neutron, neutron, proton, proton. They love to hang out. They're really a tight-knit group right here. And then what's left in the nucleus? Well, whatever it is, it's 90 here, and whatever up there it is 234. And 90, I guess 90 is thorium right there, so this would be TH. Well, this was, when we look at the particles in the nucleus, they're kind of in a well right there. You could think of a whole bunch of alpha particles. That's all there is, just a bunch of groups of neutrons and protons bouncing around in there, and they're free, but they have a barrier and they shouldn't be able to get out, but they are able to tunnel through. Their potential looks a little different because there are inverse square law, but it's still a barrier for them to get through. And you can predict how much time it takes for them to get out, which means you can predict their half-life. So you can go down and get the half-life of these for alpha decay. And this is the first way, one of the great successes of quantum mechanics early on, right here. Okay, and so this is, it's messy right here, or I don't even need this end of the thing. If I just have a barrier right here, like this, and let's say I throw a particle at it right here. So it's a free particle. It might look something like this. It's just our little free particle right here. But it doesn't have enough energy to get over the top right here through. But so normally you would just say it just bounce back when it hit the wall, but a little bit of it will make it through right here. So it is possible that you could get through this barrier by bouncing off of it. So if you're driving in your car and you lose control and you're heading for a wall, there is a slight possibility that you can make it through the wall without hurting yourself. Pop out the other side. That means you kind of went right through it, right? You tunneled through it. But I guarantee you the odds of that is pretty slim right here. Probably less than 10 to the 1 in 10 to the 500. You know, I mean, it's really unlikely. Or if you're in prison and this is the external wall and you want to get out of prison, just keep running yourself into the wall. Hopefully you can make it out the other end of the wall, out through the other side. You tunnel through right here. Or if your car is just kind of very coasting in a parking lot and there's a little speed bump right there, but you don't have enough energy to make it over the speed bump, it is possible you could still get to the other side quantum mechanically right here. Classically, it'd be impossible. Okay, this is called tunneling right here. It comes up in a lot of places, even in electronics. There's things called tunneling diodes and other things. And so they utilize this effect of tunneling right here. Okay, that's one potential I wanted to bring up. The other one is probably the most important one-dimensional potential of all, and that is the harmonic oscillator. Harmonic oscillator. Now, normally, most books spend at least a whole chapter on this, just as one-dimensional potential, used all over the place. It's the most important one. And I usually spend a lot more time on it, but this one I'm just going to give an overview because I want to get into the three-dimensionality of quantum mechanics. But the harmonic oscillator is just like a mass on a spring, and we know what the U is for that. U is, for a mass on a spring, is 1/2 kx squared. Well, I hate putting k in there because k is a spring constant. We don't have a spring in there. But we do know that for our mass on a spring, we defined omega was the square root of k over m. So k is just omega squared. It's m omega squared. So I can write this u as 1/2 m omega squared x squared. So there's the potential. And if we were to plot it out, we kind of know what it looks like. It looks like just a parabola. Right there. So there's my u as a function of x. Okay, so if we wanted to, say, guess at the solution, I mean, if we go back to Schrodinger's equation, we'd have to solve this. We'd have to solve minus h bar squared over 2m, second derivative of psi with respect to x squared, plus u of x, which is 1/2 m omega squared x squared psi of x equals e of x, e times psi. So that's Schrodinger's time-independent equation we'd have to be solving right here. But I doubt if they teach you how to solve that right here in this school. So I'm just going to tell you how we could probably guess what the solution is right here without having to work it out. First of all, let's just guess to see what the psi would look like right here. Well, first of all, since this goes off forever right here, we're going to have an infinite number of energies because you'll never be free right here. But, I don't know, let's just say our energy is right here. So there's our energy, E. Okay. I should have probably, okay. Now, what's this thing going to look like right here? Well, we know when E was bigger than U, it just kind of concaved this way and it was concave that way. And when you're out here, it was the opposite. It had to go to 0. So it looks like one solution right here would be, we know it has to go to 0 out at infinity. So it's going to probably come in like this right here. Likewise, probably do the same thing over here. And then when you're inside of here, it's going to wiggle back and forth. Well, we'll just draw it for the lowest possible state. For the lowest possible state, it has the least amount of wiggles. Well, the least amount of wiggles is, this looks like that right there. That looks like the ground state, or the lowest psi1. Or actually, for harmonic oscillator, they start at n equals 0. So this would really be the psi sub 0 state right there, the ground state. Now, if I wanted to guess what that solution was, I just have to guess now the function I can see. You know, it's got to be symmetric about the x-axis. It looks like an exponential right there. And so a good guess, maybe a good guess, would be, you know, maybe some e to the minus alpha x squared. I need a squared up there because it has to be symmetric to the two sides. It has to be a minus because it has to drop out. It has to go to 0 at both plus and minus infinity. And I need a constant up there because I can't have units up there. And then the whole area squared has got to be 1, so I guess I better need another constant right there. So that might be a good, maybe for the lowest state. How about for psi 1 or psi 0 of x? Maybe that's a good guess at the solution. Well, let's plug in and see if it works right here. I just need to find out what the second derivative is and then plug it into those two. So first, let's get the first derivative. The derivative of psi with respect to x, the derivative of this is a, and then the derivative of that is e to the minus alpha x squared times the derivative of what's up top, which is minus 2 alpha x. Okay, so there's the first derivative. And the second derivative, well, let me pull out the minus 2 alpha a, and then I just need to take the derivative of x times that. So we'll do the product rule. We'll take the first, which is e to the minus alpha x squared, times the derivative of the second, which is 1, plus the second times the derivative of the first, which is e to the minus alpha x squared times minus 2 alpha x. Okay, so there is my second derivative. And if I were to at least just multiply this thing through, we'd end up with minus 2 alpha a e to the minus alpha x squared. And then this times this is plus 2 alpha squared plus 2 alpha squared a x squared e to the minus alpha x squared. Okay, so there's the second. Now we'll plug it up into here. So we get minus h bar squared over 2m times all of this times minus 2 alpha a e to the minus alpha x squared plus 2 alpha a x squared e to the minus alpha x squared plus 1/2 m omega squared x squared psi of x times this, a, e to the minus alpha x squared, takes care of that, equals e, a, e to the minus alpha x squared. Okay, so that gives me, when I just plugged it in, and I think I can get rid of some stuff, there is an exponent, the e parts drop out. So that and that, they're in every term, so they're gone. There's an a in every term, so they're gone. Okay, so now I end up with, multiplying this through, this gives me, the 2's drop out, we get, the minuses drop out, h bar squared alpha over m. That's all I get for that one. And then times this, the 2's drop out. We get minus h bar squared alpha x squared all over m. The 2's dropped out. Plus this term, 1/2 m omega squared x squared. And I'm going to bring the e back on this side, so it's minus e equals 0. Okay, and I'm going to rewrite this again. I'm going to start with this term, and I'm going to factor out the x squared out of these two terms. So we got x squared, and I got this term, 1/2 m omega squared, 1/2 m omega squared, minus h bar squared alpha over m. Okay, that takes care of these two. And then these two terms don't have an x squared in it. So we got plus h bar squared alpha over m, but I'm going to put it in parentheses, h bar squared alpha over m minus e equals 0. Well, you'll notice right here, this is just a constant, and this is a constant. So anytime you have x squared times a constant, c1, plus c2 equals 0, this has got to be true for all x's. Then c1 has to be 0 and c2 has to be 0. It's the only way right here. So that mean that this should equal 0 and this term should equal 0. Well, if that term equals 0, then we got e equals h bar squared alpha over m. Or in this one, it tells me this term equals that term, h bar squared alpha over m. H bar squared alpha over m equals 1/2 m omega equals 1/2 m omega squared. Okay, I just want to check my, just to make sure that I have the right 1/2 h bar minus, oh, there's a 2 h bar alpha squared. When I wrote this down right here, this should have been a 2. Where did I end up with a 2? Yes, when we multiplied this thing through, I should have had a 4 there, 2 times 2. There was a 4 here, so 4. Okay, so that should have just been a 4, then which means that this term should have been a 4. Glad I saw that. And which means that this term, we got rid of it. This should be back to a 2 again, right there. So this thing should have been a 2, right there. And also, just to remind you, that was alpha squared, that's alpha squared, that's alpha squared, which means that is alpha squared. So I'm glad that's alpha squared, and that was 2. So that's the only difference. 2 h bar squared alpha. Okay, that. So now from this I can solve for alpha right here. That's what I want. So I'll move the m over there. So that makes this an m squared. We got the omega squared. We got the h bar squared. And we got the 2 times 2. I'll just keep it as 2 squared. That equals alpha squared. Or if I take the square root of both sides, alpha is equal to m omega all over 2h bar. So there's my alpha. And now if I plug my alpha up into here, I can get my eigen energy. So E is equal to h bar squared, but one of them will cancel, so I'm end up with an h bar. We have an omega. The m and the m will cancel, and we're left with a 2. So that would have been my lowest energy of the lowest state right here, 1/2 h bar omega, and the psi alpha would have been this, which means it works, which means that my state, psi of the ground state, the lowest one, would equal A, E to the minus this times x squared, minus m omega all over 2h bar x squared. And I could find my A because I could integrate this squared. If I square this and integrate from minus into infinity to plus infinity, I could get the, instead of equal to 1, I could get A, but I'm not going to do that right here. So you could normalize it. So that looks like the ground state for the harmonic oscillator, and that looks like the energy that corresponds to that ground state right there. Now, you'd also want to get the higher energy states right here. And now you say, what does it look like right here? The next higher energy look like? Well, it's probably going to look something like it's going to have an extra wiggle in there, middle of it. So how about if it looks something like, something off like that right there. It would have an extra wiggle in it right here. And now you might say, what would be your best guess on that function? Well, you notice our old function looked like this. It just kind of went around and looked like that. That was our lowest state. How do I make a function like this look like this? Well, what happens if you multiplied it by y equal x? If you took this function and multiplied it by y equal x, what it would do to the left-hand side, it would make it down negative, because this is a negative, and this one would be times it by the positive right here, and you would get this pattern right here. So the next solution up, say psi 1, would look something like it'd have some constant in front. I'm not sure if it's the same. You'd have to normalize it. E to the minus m omega over 2h bar x squared. But it'd probably have an extra x in there because it has to be anti-symmetric right here. The energy up here, I'm not going to tell you, but I'm not going to work it out, but the energy right here would just be 3/2 h bar omega. Okay, well, you look at the next one. If we look at the next state up right here, well, it's probably going to have another wiggle in it. It's going to look something like, and then go off. Well, what does this thing look like? This green one looks like your original curve times a parabola. Because if I multiply this times this, what does that do? It goes up, it goes up a little bit here, then it goes down, and then it goes back up, and then it goes back down again. So it's almost like adding some sort of a quadratic equation to this right here. And so the next one, psi 2, would be some normalization constant, maybe we'll call that one C, e to the minus m omega all over 2h bar x squared times some quadratic. I'll just write quadratic. Second order polynomial. And the next energy would be 5/2 h bar omega. And the next one, you can probably guess what the next one's going to be. It's going to be this times another polynomial that's even a higher order, the third order. And then the fourth order. So what you're going to get for the nth one, you're just going to get some constant e to the minus m omega over 2h bar x squared times some polynomial of order, of the order of like n right here. It's a special set of polynomials. Someone by the name of Hermite came up with them, and they're called Hermite polynomials. We usually call them H's, H sub n or something like that. And the very first one for the lowest state, I guess for 0, would be just 1. For the next one, it's x. For the next one, it's a quadratic. I wrote down they're not all going to be following this exactly right here. The next one is right here. X squared minus 1. The next one is x cubed minus 3x. The next one is x to the 4th minus 6x squared plus 3. And it keeps going on and on forever right here. So that's the solution and to this equation right here. So it uses what are called special functions. It needs these polynomials in there. So it's just going to be this exponential times a polynomial. This makes it die out at the end times the wiggling in between right here. And the energy for any nth orbit looks like it's just h bar omega n plus a half, where n equals 0, 1, 2. And you can see when n was 0, we got the half. When n was 1, you got the 3 halves. Then you got the 5 halves, and so on. And we can see that all of their energies are all equally spaced. So if I could draw the energies here, they would all be equally spaced. Remember, for our infinite well, they were growing this way. They went up like an n squared. And for our Bohr model, they got closer and closer together. But for the harmonic oscillator, they're all evenly spaced right there. And we could even work out our selection rules like we did for the infinite well. Remember, we said for the infinite well, it was impossible to jump by 2, I think by 2 or by 4, or by an even number. I think that's what we had right there. And we said it most likely dropped by 1, but it could drop by 3 and 5 and 7 and so on. But for the harmonic oscillator, when you worked out those that integral that tells you whether you could jump or not, you could only jump 1. So if you're right there, you can only go down 1. If you're right there, you can only drop 1. So there's a selection rule for the harmonic oscillator. The change in n has to be 1, plus or minus, I guess, but we'll just say 1. You can only drop by 1. Well, if you can only drop by 1, then what's the size of the photon that comes out right here? That is, what is E sub n plus 1 minus E sub n right here? If you just drop by 1, well, what's the spacing between these two? Well, if you just look at the spacing between these two, the difference between n plus 1 and n is just 1 right here. So that is E sub n plus 1 would be, this one right here would be h bar omega, and then you plug in n plus 1, so you'd have n plus 1 plus a half. So it'd be n plus 3 halves, right here, minus E sub n, which is h bar omega, n plus a half, n plus 1 half. If we subtract the two, the n's drop out right here, and you just get h bar omega. And if I turn that into h bar was h over 2 pi, and omega was 2 pi times the frequency. The 2 pi's drop out, hf. So it says that you're always going to get a photon, which is what? hf? Which looked a lot like, maybe now it explains the black body radiation. Because remember, what do we say in the black body radiation? The walls of the cavity oscillated kind of like a simple harmonic oscillator and gave off photons, which were E equals hf. Oh, okay, so it kind of explains a lot. This is also the way they use this a lot in this harmonic oscillator in quantum field theory right here. I'm not going to talk about it, but they use this idea of the harmonic oscillator. Every location in space is kind of is a harmonic field right here. So, okay, so this is just a little bit on our eigenfunctions, and just remember, all of these were all orthonormal to each other. So if I were to integrate psi n with psi m, it would be 1 when they're equal, it'd be 0 when they're not equal. I can make from all these eigenfunctions, I can make any picture I want for a position measurement. And so I can turn them into position measurements right here. The same way we did it for the infinite well. So it's kind of the same thing, it's just a little more complicated mathematically. Okay, so now we can get into three-dimensional quantum mechanics.